Few classes we have derived the torque speed characteristics of a DC series motor. We can write induced voltage E plus I A if we assume that the machine is unsaturated, then phi f equal to some k f into I A for series machine, and E of course is k phi f omega. Also torque equal to phi f I A. From this we derive that so from here we get R A plus R A C, and torque I A square. So, this is or these torque speed characteristics when plotted look somewhat like this. We have also seen that these torque speed characteristics can be manipulated by, let us say, changing R A plus R A C by incorporating additional resistance in the armature circuit. So, with added resistance, this point which is minus R A plus R A C plus R external by K K F goes down, and with increasing R external we can obtain characteristics like this. Another way to vary it is to vary the value of K K F. That can be done by series parallel combination of field coils. For example, if you have all field coils may be in series, here you can reconnect these field coils, and let us say in parallel. This way also we can change the torque speed characteristics of the. This has the effect of reducing the field flux. If this was phi f and this was phi f dash, then phi f dash will be less than phi f, and the torque speed characteristics will shift upwards. Let us see by a few examples how this is done. Consider a 240 volt DC series motor used for lift drive with armature current of I A equal to 40 amperes. The speed I A equal to 40 amperes, this comes to 1800 rpm. It is given that the sum of the armature resistance and series field resistance is 0.2 ohm, and also the machine is unsaturated, that is the field flux is proportional to I A. Now, let us try to find out how much R external is necessary if at a load current armature current I A equal to 10 ampere, we want N to be 3600 rpm. So, for this let us first try to find out what is E when I A equal to 40 ampere and N equal to 1800 rpm. This can be solved from V T minus I A R A plus R A C, because we have been told that without any external resistance when I A equal to 40 ampere, N equal to 1800 rpm. This comes to 240 minus 40 into 0.2 is equal to 232 volts. Since phi f is proportional to I A, we know phi f at I A equal to 10 ampere equal to 0.25 times phi f at I A equal to 40 amperes. Also, the ratio of E at I A equal to 10 ampere, N equal to 3600 RPM divided by E at I A equal to 40 ampere, N equal to 1800 RPM equal to 3600 by 1800 into phi f at I A equal to 10 amperes divided by phi f at I A equal to 40 amperes. So, this is equal to 2 into 0.25 equal to 0.5, and we know this quantity to be 232. So, E at I A equal to 10 amperes, N equal to 3600 equal to 232 into 0.5. This comes to 116 volts. Therefore, V t minus E equal to I A into R A plus R A C plus R external equal to 232 minus 116 equal to 116 volts. I A equal to 10 amperes, from which we get R external equal to 11.6 minus 0.2 equal to 11.4 ohm. So, we will have to connect an external resistance of 11.4 ohm if we want to restrict the speed to 3600 RPM when the armature current is 10 ampere. Let us now try to find out if we do not connect any external resistance and increase the load armature current to 60 ampere when the machine is connected to 240 volt, that is V t equal to 240 volts. R external equal to 0 and the loading is such that the armature current is 60 ampere. What will be the speed? Find N. It is also given that phi f at I A equal to 60 ampere equal to 1.18 times phi f at I A equal to 40 ampere. So, for that let us first find out what will be the induced voltage E. This is 240 minus 0.2 into 60 equal to 228 volts. and ampere and n equal to 1800 rpm divided by E at IA equal to 60 ampere and n, this is phi f at IA equal to 40 ampere divided by phi f at IA equal to 60 ampere into 1800 by n. So, but this is equal to 232 by 228. Therefore, from here we get n at IA equal to 60 ampere equal to 1800 by 1.18 into this is approximately 1500 rpm. So, this is how you can control the speed of a DC series motor by connecting external resistance. Let us look at some calculation regarding the other method of speed control, that is when you connect the field windings in series parallel combination. So, let us take a 4 pole DC series motor. It had 4 series connected field winding. All windings are connected in series. So, the rated terminal voltage is 250 volts. Each of these, let us say, have a turn of n. With IA equal to 20 ampere, the speed n is 600 rpm. The load torque T L on the shaft is proportional to n square. Assume that the losses, all losses are negligible, and also the magnetic circuit is unsaturated, that is phi f is proportional to field ampere turns, that is the effective series number of turns and the current through the series coil. In this particular case, N AC equal to 4 N and I AC equal to I A. However, does not have always have to be the case. Now, I connect all the coil, this all series connected coil I now change in this fashion. I have two coils connected in parallel in a group and then another two coils connected in parallel in another group, and these two groups are now connected in series. With the same load torque. Find out what will be the armature current and the speed in this case. Here I A 1 is 20 ampere, N 1 equal to, let us say this is connection 1, I A 1 is 20 ampere, N 1 equal to 600 rpm, and let us say now the speed is N 2. So, we are supposed to find out what will be I A 2 and what will be N 2. Obviously, in this case, assuming that the coils are identical, the current through each of the coil is only half the armature current. So, here the net field ampere turns N AC I AC equal to 2 into I A 2 by 2 plus N into I A 2 by 2. This is 2 N I A 2. Here it was 4 N I A 1. Therefore, the ratio of field fluxes, since phi f is proportional to N AC I AC, phi f 1 by phi f 2, this should be equal to 4 N I A 1 divided by 2 N I A 2. This is equal to 2 times I A 1 by I A 2. Also, the electromagnetic torque is proportional to phi f I A. Therefore, the torque in the first case T E 1 divided by T E 2 will be equal to phi f 1 by phi f 2 into I A 1 by I A 2. Therefore, T E 1 by T E 2 equal to 2 times I A 1 by I A 2. Whole square. But in steady state T E equal to T L, which is proportional to n square. Therefore, T E 1 by T E 2 is equal to n 1 by N2 whole square. So, 2 times IA1 by IA2 whole square equal to N1 by N2 whole square, or IA1 by IA2 equal to 1 by root 2 N1 by N2. Now, let us look at the other side. For any DC motor, we know Vt equal to Ut minus Ia Ra plus Rac. Now, in this case all losses are negligible. So, Ra plus Rac is approximately 0. So, Vt equal to E equal to k phi omega. Since Vt remains constant, we can say phi f omega equal to constant, or phi f is proportional to 1 by rpm. So, we have phi f1 by phi f2 equal to, which we have already found out to be 2 times Ia1 by Ia2. This is also equal to N2 by N1. Therefore, we have another relationship, Ia1 by Ia2 equal to half N2 by N1, and we have also seen this is equal to 1 by root 2 N1 by N2. So, we have N1 by N2 square equal to 1 by root 2, or N2 by N1 equal to 2 to the power 1/4. We know N1 equal to 600 rpm. Therefore, from here we will find out N2 to be equal to 2 to the power 1/4 into 600 equal to 714 rpm. How about Ia1 and Ia2? We know so Ia2 equal to 2 times Ia1 into N1 by N2, comes to 2 into Ia1 is 20 amperes into 600 by 714, this comes to 33.6 amperes. We see that with a given load characteristics, by connecting the configurations, changing the configurations of the field winding, we can change the speed of the DC series motor. However, it should be noted that we can obtain only discrete values of speed. The speed cannot be changed in a continuous fashion. In order to have a continuous speed change, we should use either a continuously variable armature resistance, or if we want efficient operation, this DC series motor can be fed from a variable DC voltage source such as a chopper. Like DC shunt motors, it is also necessary to find out experimentally the losses and efficiency of DC series motors. In case of DC shunt motor, we have seen there are two tests. One is called the Swinburne test, which is basically a no load test, which find out the no load rotational losses and constant losses, and then there was Hopkinson test, which is a regenerative test to find out the efficiency and losses at different loading of the DC machine. We would like to do similar tests on a DC series motor. However, one problem is that a DC series motor, a equivalent test to Swinburne test is not possible, because at no load the DC series motor speed tends to become very high. So, it is not advisable to operate the motor at no load. Therefore, we have to find out the losses by load testing only. Here also there are some difficulties in doing back to back test. So, the motor or the machine has to be actually loaded to do this test, and the test is called the field test. Fields test. Like Hopkinson test for shunt motors, here also you need two identical DC series motors, which are mechanically coupled, one of them act as a motor, another act as a generator, but the difference is the generator does not feed the motor, there is no back to back connection, rather the generator feeds a external load, variable load. The motor field winding and the generator field winding are connected in series. And both in series with the motor armature. You measure the terminal voltage here, and also the voltage across the motor terminal, as well as the armature current of the motor, the armature current of the generator, and the load voltage. So, the set, these are two identical DC series motor, and since their field windings are connected in series, the iron loss and the no load rotational loss of both the motors are assumed to be same. The readings that we take are V t equal to supply voltage this is I, the motor supply current, this is I 1 the generator output current, and this is V 1 the load voltage. Generator output current. Now, the power input to the set equal to V T I, and power output of the generator equal to V 1 I 1. So, total loss equal to W is V T I minus V 1 I 1. I square R loss is given by I square into motor armature resistance plus motor series field resistance plus generator series field resistance plus generator armature copper loss. Now, these resistances can be individually found by voltage drop method, those components. So, the no load iron and rotational losses P I plus P W friction and windage losses, this is equal to total loss W minus I square R loss. So, this is W 0, no load rotational losses. So, no load rotational losses, since these are identical machine, we are saying no load rotational losses of each machine this will be W 0 by 2. Motor input power is this V m multiplied by Vmi. So, motor efficiency will be Vmi plus of course I square RSM. One minus W0 by 2 plus I square this can also be written as what about the generator input? This we can say new motor. The generator input this is equal to V1 I1 plus this is the output of the generator W0 by 2, this is the no load rotational losses plus I square R S G, this is the series field loss of the generator plus R A G, this is the armature copper loss of the generator. So, generator efficiency mu G equal to 1 minus losses in the generator divided by the total input of the generator. So, this is how we can find out the losses and efficiency of the individual machines from field test. Let us look at an example to see how exactly this is done. For that, let us consider field test on two identical DC series motor. The motor, for the motor, the data is like this: the armature current into 60 ampere, armature voltage equal to 500 volts, series field voltage at I A equal to 60 ampere, this comes to 40 volts. For the generator, terminal voltage is 450 volts, output current equal to 46 amperes, and field voltage across field winding again at I A equal to 60 amperes, this comes to also 40 volt. So, find out what is motor efficiency and what is generator efficiency from this data. Let us see how we use this data to find out the motor and the generator efficiency. So, what is the total power input to the set? P input, this is equal to the voltage across the motor armature plus voltage across the motor series field plus voltage across the generator series field into the armature current 60 ampere. This comes to 34,800 watts. Generator output, E out, this is generator terminal voltage 450 volt into generator output current 46 amperes, this comes to 20,700 watts. So, P loss equal to P input minus P out, this comes to 14,100 watts. So, no load rotational losses W 0 by 2 equal to no load rotational losses is P loss by 2. This comes to of course, from here we will have to first subtract the ohmic losses. This is the total loss, I square R loss will come to 60 square into 0.25 plus 60 into 40 plus 40, this is the field loss, plus 46 square into 0.25, where this 0.25 is the armature resistance of both the motor and the generator. This comes to some 30 watt. So, the no load rotational loss of both the machine W0 equal to P loss minus I square R loss. This comes to 14,100 minus 6230 watts. So, W0 by 2, which is no load rotational loss, this comes to 3935 watts. Motor power input equal to 500 is the armature voltage plus 40 volt is the field voltage into 60, this comes to 32,400 watts. Motor loss equal to armature circuit loss plus field circuit loss, ohmic loss plus no load rotational losses, this comes to 5 watts. So, motor efficiency nu m equal to 1 minus 7235 by 32,400 into 100, this comes to 77.68%. So, total generator loss this is again 46 square into 0.25 plus 5, this comes to 6865 watts. So, generator input equal to generator output, which was 20,700 plus 6865 equal to 27,005 watts. So, generator efficiency nu G equal to 1 minus 6865 divided by 27,005 into 100, this comes to 74.49%. Thank you.